Another derivative which is extremely important is the derivative of the exponential function. Not only is this derivative important, it's actually quite easy to remember too. Its derivative is just itself. That is, the derivative of e to the x is just e to the x. Visually, this can be interpreted as saying that the slope of the curve y equals e to the x is equal to its value at every point. In other words, if we move x units to the right and consider the corresponding point along the curve, then the slope at this point is the same as the y value at this point. Both are equal to e to the x. One way of interpreting this is by saying that the slope of the curve is growing just as fast as the values. In particular, if we look at the point x equals 0, then the value of the function there is e to the 0, which is 1. Because this value is the same as the slope, this means that the slope of the graph of e to the x has value 1 at x equals 0, or at the y-intercept. If you remember, this is actually how we defined the number e in the first place. What we said at the time was that e is that unique base for which the slope of the tangent line at the y-intercept is equal to 1. One way of expressing this slope is by using the definition of the derivative involving the difference quotient. In particular, 1, which is the slope, should be equal to the value of the derivative at x equals 0. Using the definition involving the limit then, the derivative at x equals 0 can be written as the limit as h goes to 0 of the quantity e to the 0 plus h minus e to the 0 all over h. Since e to the 0 is just 1, this difference quotient just becomes e to the h minus 1 all over h. What this means is therefore that our definition of e as that unique base which has slope 1 at the y-intercept implies that this limit on the right is equal to 1. Just from assuming this single limit then, the full derivative of e to the x can be determined. Indeed, the relevant difference quotient for the derivative of e to the x at the point x is just e to the x plus h minus e to the x all over h. And by a rule of exponents, we can rewrite the first term as e to the x times e to the h. Once we've done so, we see that we can factor out a term of e to the x. And since this term doesn't involve the variable h at all, we can actually pull this factor outside of the limit. What we obtain then is e to the x times the limit of e to the h minus 1 all over h. Notice that this limit is the same as the one from before, the value of which we said is equal to 1, according to the definition of e as that unique base which has slope 1 at its y-intercept. What we obtain then in total is that the derivative of e to the x at the point x is equal to e to the x times 1, or e to the x, as we had previously asserted. Now, if we use a different base in our exponential function, the derivative changes. Specifically, if b denotes the base of the exponential function f of x equals b to the x, then the derivative of f is given by f prime of x equals b to the x times the natural log of the number b. Notice that in this general case, the derivative is almost equal to the original function, but the only difference is that it's multiplied by a factor of the natural log of b. In particular, when b is the natural number e, then this factor becomes 1 since the natural log of e is just 1. But for other bases, this factor of the natural log of b is some other number that's not equal to 1, and this other number is actually the value of the slope of the graph of b to the x at the y-intercept. Indeed, the slope at the y-intercept is just the value of the derivative at x equals 0, which, according to the rule, is b to the 0 times the natural log of b, which is just the natural log of b.